All right, good morning. I hope you're hearing my audio. I'm trying a new microphone, so if there's massive problems, I'll just switch back to my built-in microphone. This one I'm wearing on a clip here, so we'll see if it works. I struggled with it a lot to get it to work on my Linux machine. It's quite frustrating. So let me change a couple things and remind us where we're at. Good morning, everybody. Thank you for being here. You're seeing a still picture and not my actual what I want to share with you. So let me see what's kill that screen. So sorry, I'm a little slow to get going this morning. All right, there's that thing. Okay, there it goes. This is where we left off on Thursday. Was we had this circuit in sort of testing mode. That's lab 9.1. So the goal today is to work through the questions in this week's homework and then to finish lab 9.2. So yeah, we're just gonna forever fight the audio problem, and I'm sorry about that. I just cannot. I don't have the resources, and I cannot get my hands on decent audio equipment, and the college is not likely to pay for that stuff anyway. So I'll try moving the microphone clip down a little bit on my shirt. And I'm adjusted down the gain, and I'm trying to talk quietly, so I'm kind of just watching my mic monitor and trying to make sure it's not going too high, but I also know that there's a little bit of lag on Twitch. Okay, so yeah, I've tried my best. Anyway, so this is where we left off. We have that's lab 9.1, which has 2, 3, 4, 5 LEDs on it, and we're just flashing it as part 1 of lab 9 because that's a way to test that the circuit's wired up correctly. So that all looks good, so now we can kind of work on the homework questions, and then we'll do part 2 of lab 9 as our first experiment with doing decision making. So the big star of the show this week is what does decision making look like in ARM assembly? So in other words, how do we do if else or switch type code in ARM assembly? So the main instructions, the one that we're going to use today is the compare instruction. So you compare two things. You have either one register and a value or two registers. But anyway, you run a compare. You compare an X and a Y. And then for now, what we're going to do is branch on the result of the comparison. And branches, let me move this way out here. So this is the way this is always going to be set up. You're going to run a comparison, and then you're immediately after going to do a branch, at least for today, and then we'll get more sophisticated about it. And you branch based on the comparison. So what you have to get used to in assembly is that it's 2 steps to complete logic, and sometimes more. So in a high level language, you do something like if x is equal to y, then do things. And in assembly, you're going to compare x and y, and then you're going to do in this case, if they're equal, you're going to cause the code to jump somewhere based on that result. Or sometimes you'll find that it's backwards. Now, it's a lot easier to see how this works in an actual program, but the takeaway here is that if you want to do decision making, it takes 2 steps at least to do it in assembly. You run a comparison instruction, and then you immediately act on the result of that comparison. Whereas in a high-level language, that feels like it's all in one step. I do a comparison, and then that just flows into a block that acts based on the outcome of the comparison. In assembly language, we do a comparison, and then we have to cause the execution of the program to go somewhere based on that outcome. I'll explain it when we do part 2 of Lab 9, and hopefully it makes more sense that way. So that's the main ones that we're going to see today, is compare. There's also, though, so in addition to the compare instruction, we also have the test for equality instruction. It's a little bit different than compare, but it pretty much does what you would think it is, which is to test 2 things to see if they are equivalent. And then we also have the test instruction, which allows us to test to see if specific bits are set. So compare and test equal allow us to compare 2 values with each other. And then the TST, or the test instruction, allows us to look at one value and see if specific bits in it are set, are ones. And then we use branches, which is the one that we're going to use today. Or in ARM, what we call conditional instructions, that we'll use. We'll try those later. Or conditional instructions to act based on the outcome of the comparison, the test for equality, or the test of bits. All right, so that's a pretty rough introduction to that, and again, it's a lot easier to understand if you see it working in a program. So that's what we're going to go for today, is answer some questions on the homework and then bring up part 2 of Lab 9 and try out some comparisons and some branches. So let's hit the homework first. I want that higher up. Okay, so I'm going to hit the homework questions first and get those knocked out, because those answers are useful to us in the lab today. Okay, so I'm just going to share with you the words that I got from these readings that I linked. So the first question in ARM assembly, what is a branch? A branch is a break in the sequential flow of instructions that the prosecutor is executing. And what I mean by that is so the code is executing through a sequence of instructions. When it encounters a branch, there's a chance that it's either going to leap forward, skipping past some set of instructions in the sequence, or it's going to leap backwards and actually repeat a set of instructions in the sequence. What branches look like in high-level languages is if-else or switch statements and loops. So if-else statements and loop type statements in high-level programming are doing branching. They're breaking the sequential flow of execution that the processor is trying to do. And then I added this language, and also because I think it helps. Some architectures call branches jumps, and that word helps some people. So on Intel, they call these instructions jump instructions, whereas in ARM they call them branch instructions. But for some people, the idea of jumping back in time or backward in the sequence, or jumping ahead across the sequence of instructions is helpful. And again, you're going to see Lab 9 Part 2 where we'll actually do some of these things. Okay, so the branch instruction by itself is just the B instruction, and branches have to be given locations to branch to. Now, you don't do this in high-level programming unless you've ever written a go-to. But in assembly programming, when you need to branch or jump in Intel terms to some location in your sequence of instructions, you actually label the location so that you can branch to it. So a branch instruction would look like this. You'd have a B, which means branch, and then you'd have some location that you have labeled in your code to branch to. And again, in Lab 9.2, we're going to see how this works. We call that, by the way, an unconditional branch. And an unconditional branch means that there was no condition, like we didn't do a comparison between two values before we decided to branch. We just branched, and you'll see where we use that. We use it quite a bit. Okay, let's see. And then I also added this part in my terms. So when the processor encounters a branch, it always branches or jumps to the designated point. So it just does it. There's no only if the two values were equivalent or only if x was greater than y. A B means the branch is happening. And I'm not sure if we're going to see it in today's code, but I'll try to put one in there. That's the most basic of the branching instructions, though, is the unconditional branch. Okay, so I just mentioned this, but how does an assembly language programmer represent where a branch goes to, the destination of a branch? So here's the words that I got. Wrong place. So in assembly language, it is possible and desirable, and in fact, I don't even know if there's another way to do it, but you represent where a branch goes to by a symbolic label. So in my question number 2 answer above, the symbolic label is some location. And you'll see how we put but you actually put those labels in your code that give you branching targets. And we'll do several of those in the second part of Lab 9, and then we'll do more on Thursday in Lab 10. The way that an assembly programmer represents the destination of a branch is with a symbolic label, we call it. And then the second part of this question is, what does the symbolic label actually do? So the symbolic label is actually something that the assembler, you can think of it as our compiler. The compiler translates the label into a memory address that allows the flow of instruction to jump or branch to that memory address. And you're going to see this again here in just a moment when we work on part 2 of Lab 9. So the nice thing about symbolic labels is that you, the programmer, can just use words to describe a location, and then the assembler or compiler translates your symbolic label words into an instruction address that it can use to jump to and begin execution. Let me go back to, oh no, I won't do that just yet. Let's just keep answering questions. This is hard to understand until you've experienced it in code, so hopefully the experience in code here in a bit is going to help. Okay, so how do comparison operations actually work? These are just extra details. It doesn't, at the end of the day, actually matter. You just learn how to craft your logic. So how do I make an if statement here, or how do I write a loop here? You learn to create your decisions in loops. And you don't really worry a whole lot most of the time about how do the comparisons actually work. But just so you know, the way they actually work is that the processor performs arithmetic or logical operations and then sets flags in the program status register. So a really simple example of that is the CMP, or the compare instruction. The processor actually just subtracts one of those values from another and then sets, for example, the 0 flag would be set if they are equivalent. The negative value would be set if the second value is larger than the first value, and so on. You never have to worry about these things in code. You just use the symbols to represent the results of comparisons, which we're going to look at in code here in a second. But what the processor actually does is it takes the two values in your comparison or your test for equality, and it applies either an arithmetic or a logical operation. So the TEQ instruction, as an example, and I'm not writing this down because it's not really important to memorize it. The TEQ instruction actually uses exclusive OR on its values, whereas the CMP, the compare operation, uses subtraction. But what comparisons do is they set status flag. They do status flag settings, and then the branch instructions are written with symbols to check those status flags to see what the result was. Okay, there's two parts to this question. Do these operations store the results of their underlying operations? That's more important. So this second part of this question is actually the important part for you, the assembly programmer, to know. And the answer to the second part of that question is, if I can get it to show where I want it, there we go. No. The result of a compare or a TEQ or a TST instruction is not stored anywhere. The only place where you can actually discover the result of a comparison instruction is by writing code that tests the status flags. And I will explain to you when that's happening when we're doing Lab 9 Part 2, and then on Thursday we'll go through the same description of writing comparison instructions, writing branching instructions that use the result of the comparisons, and I'll point out to you where the status flags come into play, even though you can't actually see them when you're writing code. But when you do a compare instruction, there's no result of the comparison stored anywhere other than in the status register. Okay, so number 5, what comparison operation would be used for a normal comparison? And I assume I put normal because that was in the reading, the values in two registers. So if I want to compare registers R1 and R2, those values, then I would use a compare instruction. And then, just so you have some sense, what the processor actually does for that is it performs the arithmetic operation R1 minus R2. and then sets program status register flags based on the result. So if R1 minus R2 is 0, then the Z or 0 flag would be set, which would mean equality. If R2 is greater than R1, then the result will be negative, and the negative is set, and so on. You don't really have to, when you're coding, worry about what the flags actually look like, because ARM assembly has some sort of easier to remember ways of coding for those results. But that's how the processor actually sort of determines a result, is by subtracting R2 from R1 and then setting the appropriate flags. Okay, so number 6, the comparison operation to test for specific bits. So specific bits is the TST instruction. And we would have the value that we're testing to see which bits that are in. So let's say we want to see which specific bits are set in R2. We would load up, or in R1 rather, sorry. So we want to, that's what happened. We want to see what bits are set in, well, let me just do it so I can explain it better. So if I wrote my instruction like this, I'm using R2 as the bits I want to check for, and then I want R1 to be where I'm checking those bits. So this test instruction means test in R1 to see if the bits in R2 that R2 expresses are set, if that makes some kind of sense. But again, you're going to see this in how it's used, so it makes a huge difference once you've actually used it in code to understand how it works. The point really here is to test for specific bits, you use the TST instruction. In the processor, we'd say uses R2 as a bit mask on R1. A bit mask is kind of just like a bit filter. Probably an AND instruction, but anyway, let's not get too obsessed with that one because we're not going to use that one super soon. But R1 is where we want to see which bits are set, and R2 allows us to sort of specify which bits we're interested in. Hopefully that makes some sense. Who's here this morning? So a bunch of you are here. Good morning, everybody, if you didn't get a good morning from me earlier. Okay. 7. That one's harder to understand until you've used it, so that's the answer. Don't worry about it tons. Okay, so the simplest way to set, shouldn't that be PSR? Anyway, what's the simplest way to set the condition flags prior to branching? Is to use one of the 3 comparison operations. So if you, this is kind of a trick question just to try to remind you that what you're doing when you're running a comparison is you're actually causing the processor to set condition flags. And then after you do the comparison, you write instructions that take advantage of the current values in the condition flags to do things, usually branching. Okay, so the answer to number 7, what's the simplest way to set those condition flags, is to run one of the comparison operations, which in ARM are, there's others, but I'll say such as instead. Such as comparison, test for equality, or the bit testing instruction. The little pauses, by the way, are me going back and seeing if any questions have popped up. Okay, So number 8 is just to expose you to the next step. So if you ran a comparison, let's just say of R1 and R2, what's going to happen is the processor is going to do an R1 minus R2, and then it's going to set some condition flags in the program status register. So how do I actually test for that? The way you test for that, at least for today, is going to be you're going to branch based on some condition. In this case, what if the two are equivalent? There's actually then sort of a mnemonic, we'd call it, but a letter code that represents that condition. So I don't worry about, was it the negative flag, was it the 0 flag, was it the carry flag, was it the overflow flag? I just write branch if equivalent, and that automatically tests the correct status or condition flags for me. And then branching instructions, you have to provide them with a location that's been labeled in your code. And you're going to see this here in just a moment in part 2 of Lab 9. So this BEQ to some location, that's how you test the result of the comparison. I'm going to note here, by the way, that branch needs to happen immediately after that comparison, because if you don't do it immediately after the comparison, the status flags, the condition flags can change, can be changed by other instructions, and they may not have the same meaning anymore. So you run a comparison, and then you immediately do a branch that uses the code to check the appropriate condition flags. And notice I don't have to worry about which program status register bits to test. I just use the EQ mnemonic, and that gets me to the right place. I'm going to finish these, and then I'm going to follow one of the links and show you more of this stuff. Okay, so that's really the answer. Is for this particular question, what if they were equivalent? Well, then I would branch when they're equivalent to some location I've labeled in my code. Okay, so now we're at this sort of little breakpoint. The branch instruction that branches, so if we were to run a comparison, what branch instruction or code would we use to check if the result was that R1 is less than R2? So I'm going to scroll up. I'll come back down here in a second, but I'm going to scroll up, and I'm going to follow, I think it's link number 5. Yeah. Okay, so let me look at link number 4 also and see if that one's easier to digest. It is not. Okay, so I'm going to show you link number 5. So what questions 8 and 9 are about is beginning to expose you to how do you actually code for the results of comparisons. So if you're looking to see if a result was equivalency, then the code is EQ, branch on equivalency. In this case, we want to know, is R1 less than R2, assuming they're both unsigned integers. So let's go over to this page. Hopefully you're seeing that. I've got a lot of stuff going on my screen. Okay, you do. And look for the code. So here's one that's uncoded. That's the unconditional branch. It turns out that there's actually a 2-letter code, AL, branch always, which is an unconditional branch. I don't know why they have both, but I guess someone liked it. Here's the branch on equivalency that we just used. The comparison discovered that the two values were equal. Notice, by the way, there's a branch when two things are not equal. So what we're looking for is a less than with unsigned integers. So I don't care about carry out. I don't care about carry. So here's an unsigned comparison that gave a higher or same as, which we would think of as greater than or equal to. Well, that's not what we want. Here's an unsigned comparison that gave lower than. That means R1 is less than R2. That's what we want. So if we go over here, we see that the two-letter code for less than or lower than is BLO. So the answer to number 9 is BLO, which means that the prior comparison yielded a result that the first argument was lower than the second argument. In other words, R1 is less than R2, which is a lot to take in. Hold on, need to sip the drink. Okay. Now we haven't done this yet, but you're going to see something called conditional execution. We don't have to worry about this yet, but you're going to end up using it a lot. So I'm just sort of exposing you to the idea that this idea exists, and then we'll see how it actually plays out. But ARM has this super cool feature where you can actually attach the results of comparisons to other instructions. I'll just give you an example real quick. The answer to number 10 is all of them. Pretty much all. In fact, I think it's true that all ARM instructions can be conditionally executed. So let me just give you a quick example of what that might be. So if I compare R1 and R2, so let's just set up this little scenario so you can kind of understand what this means. So you can actually make instructions dependent on the comparisons that precede them. So as an example, I'm going to compare R1 and R2, and then I only want to compare R3 and R4 if R1 is greater than or equal to R2. So if I go back to this page, the greater than or equal to, higher or same. So higher or same. So I can actually do this. I can actually attach the result of that prior comparison to yet another comparison. That's an example of a conditionally executed instruction in ARM, which means that you can take those two-letter codes representing the results of comparisons, you can attach them to future instructions that then means they're only executed in the case that the prior comparison had that result. So then I can even do something like this. So it looks really crazy at first, but you'll find it's very powerful, and you will come to really love it because it makes this part of writing assembly on ARM much more pleasurable. You have a lot less extra code to deal with. So we're not doing any of this stuff right now. I'm just showing you an example of what we mean by a conditionally executed instruction. They use the same two-letter codes as the branching instructions do, but you attach the two-letter code to the instruction that you want to be conditionally executed. It's pretty cool. But the answer ultimately to that question is which instructions can be conditionally executed? All of them can be. You can attach those two-letter codes to all of the ARM instructions and build yourself up quite elaborate bits of logic. Okay. So I'm about to transition into part 2 of Lab 9. So I'm going to rearrange my desktop. I'm going to go get myself some water real quick. So we're going to take like a 1 or 2 minute break while I go grab some water for my throat. So I'm going to hide the browser, and let's see, I'm going to get rid of this thing for now. Okay. Get that going. All right, so let me get set up for all of that stuff here before I. Okay, so there's the. Use some kind of markdown style. Hopefully I'm right that lab 10 is just a one-parter. Trying to get my website. Okay, there's lag happening. I can see it. Apologies if you're having a lag issue. Yeah. Okay. All right, I just had a lag. I had to refresh my Twitch page just to see what's going on, so I lost chat up to that moment. Anyway, I've highlighted here at the top of the screen before I run off to get water what's due this week. I will come back and repeat this at the end of the session. So what's due this week is homework 9. Lab 9, you only really need to turn in main2.s. You need to make sure it's functioning properly on your circuit before you do that, please, and make sure it compiles. I still get some submissions that don't compile and submissions that don't actually make the circuit function properly, so that's sort of your task. I'm giving you all of the code you need, and then your problem is to make sure that it works. So we're going to do lab 9 main2.s right now after I get some water, and then lab 10 we're going to do on Thursday. So I think we'll probably get through lab 9 part 2 pretty quickly here. So apologies, I'm going to go get some water and then I'll be right back, maybe a minute or so. All right, hopefully the audio is still working. This new mic is not, I thought it was going to be all of that and then some, but struggling to get it to work with my Linux machine, so that's kind of a bummer. Okay, so part 2 of Lab 9 is our first time that we get to do some decision making in code, and what we want to do is basically, let me get my pen, we want to turn on these lights in sequence, so it'll be light 1 is on, then light 2 is on, then light 3 is on, then light 4 is on, then light 5 is on, as opposed to just all flashing at once, and we're going to use comparisons and branching to do that. So let's load up main2.s of this lab. And then work our way down through it. Okay, so what you're seeing on the screen here, that's what we did last Thursday. We wired up, we added one LED from the week before, and then we wired it, and then we wrote the main1.s program just to check to make sure all the lights in fact do blink, and they do, so we're all good to go. Alright, so now I'm just going to do the same thing I did for part 1. I'm going to start looking through the code for the numbered elements that tell me where I need to do things. Okay, so make sure you're seeing, okay, you are, so number 1 here. So I'm going to use LDR to load the pin settings into R4. So the trick is I need to know the pin settings here, something in hex. And I need to pay attention to which setup register I'm working with at the time. So for part 1, I'm working on the mode register, so I need to remember that the mode register is 2-bit settings for every pin. And the setting that I want is 0, 1 for all the pins that I want to be doing output on. So 0, 1 on the output pins. Then I have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And then I just start populating. Zeros for the ones I don't care about. So this is mode, 2 bits per pin. So this is a 0, those first 2, and I don't care about those, so 0, 0. I don't care about A1, 0, 0. I don't care about A2, 0, 0. I don't care about A3, 0, 0. Don't care about A4, 0, 0. I do care about A5, and I want that to be 0, 1. I do care about A6, 0, 1. A7, 0, 1. A8, 0, 1. A9, 0, 1. And then all the nibbles further left, I can just leave those out of the mix. So that's my value that I need. So this first nibble, that's 5. The second nibble is 5. And then 2 zeros. It feels wrong. 5, 6, 7, 8, 9. But I think that's right. 5,500. Correct me in chat if you see that I make a mistake. To the 0 to the first 2 squared, that should be 5,500. Okay, so notice here that 55,400. Oh, thank you. I missed there. Yeah, there's a whole nibble I didn't account for there. Thank you. It just I knew something felt wrong. Thank you, Vince. Just forgot that nibble right there. There should be 5. Okay, now we're all good. Okay, so this is a little bit different because the first thing we did was we loaded the pin settings into a register. And now we're going to use those pin settings to set R2. And settings, remember, are OR. So I'm going to OR R2 with R4 R4 being the register that has my pin settings in it. I'm just going to space those over so they line up pretty. So setting bits is the OR instruction. I'm setting bits in R2, and I'm using the value in R4, which is the value that I just created with that load instruction. All right, that's 1 and 2. 3, so it recommends that I use R5 as a counter, and it says to initialize it at 1. All that really means is moving the value 1 into R5, and I will use R5 as a counter. Remember that you can use the pound symbol if you want to, but it's optional, so that's up to you. You can also do it as hex or as binary, totally up to you. For things like this, I don't see any advantage of not using decimal, because I can think of counters better in decimal anyway. But anyway, that's all we mean by initialize a counter in assembly, is to move a value there. Okay, so now we get to do some logic, and there's a whole bunch. So some of this at first is going to feel a little bit counterintuitive, because high-level decision making is, you've gotten so used to it, and then sort of the differences in assembly can feel a little bit awkward at first. But it is telling me use the compare instruction with branches to do the following. I've since made a change here, by the way. When it says toggle A9 on, I really just mean toggle A9. But the keyword there is toggle, which hopefully you remember is the exclusive OR instruction. Okay, so there's a few things going on here. So the first thing is I want to see if R5 is equivalent to 1. And the way I'm going to do that is by comparing R5 with the immediate value 1. That's all I'm going to do. Okay, now here's how I do assembly style decision making. What I usually do is sort of the opposite of what your brain might think from high level programming. But what I usually do is I write a branch instruction for the counter of what I was looking for. So in other words, what I'm looking for is that they are equivalent. So I'm going to branch when they're not. This is actually how high-level decisions tend to work. I'm going to branch when they are not equivalent, and I'm going to say, let's say case 2. And then you're about to see how that works. So if R5 is not equivalent to 1, I'm going to branch to a label that I'm about to place in my code called case 2. And that is right here. I put my labels on the left margin because I find it easier to find them. So there's the case 2 label. You'll notice it has a colon on it, whereas when I'm branching to it, I just use the label name. So if R5 is not equivalent to 1, then I'm going to break the normal flow of execution and cause the program to jump to this label. So these are symbolic labels. What the assembler actually does is turn them into addresses in the sequence of instructions, but that's it. So if those are not equivalent, I'm jumping or branching to this location. These labels don't actually do anything. They don't cause anything to execute. They're just a place that you can branch to or jump to. But otherwise they don't do anything. They're just a location to get to. So the question is, I'm going to just move this over a little bit. If I get here, if I get to the line right after this branch, that means the branch did not happen. So I'm going to branch not equal, which is going to cause the flow of execution to jump to line 71. But if they are equal, then that branch won't happen, which means that I'm going to get here. So in other words, the way I get to line 68 is they were equal. So that's what I mean sort of by it's counterintuitive. I'm actually writing my branch statement to not do what I want to do when these are equivalent. So if I don't branch, then I do what I want to do when they're equivalent. And that is to toggle A9. So I'm going to EOR something here. So the trick is I need to see where the values live. So how do I toggle A9? Well, let's look up the register of interest is the output data register, and I notice that I've loaded the address of the output data register in R3. I dereference that address to get a value in R2. So R2 has the value that I need to do the toggle on. So toggling A9. So there's a lot going on here. Toggling A9. So output data register now means 1 bit. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And I'm interested in A9. So not to the 0 to the first, 2 squared, 2 cubed. Not to the fourth, not to the fifth, not 6, not 7, not 8, but 9. That's the one I want to change. So there's my value, that's 2. So that's my value to toggle A9. And then I'm going to immediately store that back. So I'm going to take that value I just manipulated and store it back into R3 dereferenced, which takes it all the way back to the ODR register. So that is what a if R5 equals 1 looks like. Now there's one other thing to do, because I'm basically setting up like an if, else if kind of statement. So here's the next problem. After I am finished with this sequence for R5 equals 1, if I don't do anything, the program is going to flow to the next instruction that it can execute. So it's just going to keep going and keep going. The labels don't do anything. The program will just flow right past the labels and do the next available thing. So when you have a setup like this, when you're done and you need out, you do an unconditional branch. So once I've done my R5 equals 0 sequence, I need to get the heck out of my if-else if statement, or my switch statement if you like. And to do that, it's already instructed me actually to do that by branching to a label. So once I'm done with my R5 equals 1, I'm going to unconditionally branch, because I am done, all the way down to this label, the start delay label. And then as I do that, I'm noticing something I don't like about case 2. So notice how start delay starts with an underscore. That doesn't have to be that way. I just happen to like the way that looks for labels. So I'm going to just be consistent about that and start all my label names with an underscore. That's just because I think it looks cool that way. Okay, so hopefully that's making some kind of sense. If R5 is equal to 1, I will not do this branch because it's a not equal branch. I will instead just continue going. I'll do my EOR, which toggles A9. I'll store that back into the output register so that the light comes on. And then I will branch to the start delay label, which takes me past all of these things all the way down to here. So whatever else comes in here will get jumped right over or branched across. Okay, so let's work on part 2. So this is sort of a else if part, so I'm interested in is R5 equivalent to 2, so I'm going to compare R5 and 2 this time. If they're not equal, then I'm going to go ahead and let the program try 3. Go to case 3. So just like I did before, if R5 was not equal to 1, then I try 2. If R5 is not equal to 2, I will try 3. So I'll go ahead and put my label in for that. This spacing, by the way, that I'm doing right here is just to make it easier to kind of see that this is kind of like an if statement. So if these are not equivalent, then I'm going to jump over and try 3. If they are equivalent, then the branch won't happen, and I will do what I want to do for case 3, which is to toggle A8. So A8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I don't care about 0, 1, 2, or 3. I don't care about 4, 5, 6, or 7. I do care about 8. And then I need to finish that nibble. So there's my toggling value for A8. So to toggle I use EOR. I know I'm affecting the value in register R2. This time it is 1, 0, 0. I'll store that back into the appropriate register, and then I will get the heck out of here. Because if it's 2, then there's no need to try 3 or 4 or 5, so I will do what's required to do when it's 2, and then branch all the way across to pick up in this other section of the program. So I'm going to pick up the pace a little bit. Again, just like I've been doing for every session, I post the videos. I'm running a little long here, so thanks for your patience. But I'm going to pick up the pace, finish these. You can always watch the video and pause it. I'll talk through what I'm doing, but I'm going to do it fast, or faster. So case 3. So now I'm comparing R5 with 3. Remember, R5 is my counter. Same approach though. If they're not equal, then let's try 4. So I'll set up for that. If they were equal, then I'm going to toggle A7. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. A7, which is that one. So my toggling value is 8 and a 0. Store that back so that it actually alters the circuit, and then get the heck out of here. Branch to that start delay label down here so that I skip over all that stuff. Case 4. If it's not equal to case 4, then I will try 5. But if it is equal, then I have work to do. So this is toggle A6, so 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I don't care about any of these. I do care about, that's 2 to the 4th, 2 to the 5th, 2 to the 6th. That's the one that I want. So my toggle value is 40. Store that so that it hits the circuit, and then get the heck out of here. Case 5. So I'm going to make myself a little bigger than 5 label. That's right here. Come back to that in a second. So toggle A5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's 0, 1, 2, and 3. That's 4, 5 right there. So my exclusive OR-ing value is 0x20 this time. Store that back so that it changes the circuit, and then get the heck out of here. R5 greater than 5. So this is kind of like the else part, or the default part of a switch. If I get here, I don't have to do a comparison at this point. I already know it's not 1, it's not 2, it's not 3, it's not 4, and it's not 5, so it has to be greater than 5. Tells me to reset R5 to 0, so I don't have any comparison to do here. I already know that my logic could not have brought me here if R5 was anything other than... Now there's a reason why I'm setting it to 0 here, which I'll show you in a second. But anyway, I'm going to reset it to 0 by moving 0 into it. I'm going to ignore 9b for a second. So that's all that is. I don't have to do any branching from here, because if I don't do any branching, then the program will just flow. It'll come past this start delay label, but since that doesn't actually do anything, it'll just keep going. And then number 10 says increment the counter right here. So we've done that actually. That's just add 1 to R5. So the reason why I made R5 0 up here is because I knew I was going to increment it. So this is effectively, if I had reset it to 1 here, it would become 2, and then my logic would be messed up a little. So I made it 0 here, knowing that an increment was coming. And that should be the circuit. This is main2.s, so pay attention for that. Let's try it out. So let me go grab the sequence of instructions. So just be careful here. I'm going to do this part just to remind you. I was just working on main2.s, so make sure that you alter that first step in the recipe to be main2.s, because that's where the code is. You don't have to alter any of the other steps, just that main2 step. B start delay on line 72. Oh, I put the colon here, so you don't use the colon on the branching part. You only use the colon when you're actually using the label as a locator, but not for the branching part. So I accidentally put a colon right there on line 72, and that's wrong. The colons only go where the labels actually mark a spot. So again, I'm going to try the compiler again, main2, that's the file in question. All right, so all's good so far anyway. Do the second step. The second step I don't have to change. It's only the first step that has to be main2.s or main1.s. All the other steps can just be as they are. What? Oh, I didn't copy all of it. I copied just the RM. I'm going to start up OpenOCD in another tab. Alright, so I have OpenOCD running. Then I'll do the GDB stuff, which I just messed up. Okay, so where are we at? And can you see my screen? It's a little low, isn't it? All right, so I'm just following the recipe though. File main.elf, target remote local host, load, so burn the chip, monitor reset halt, so reboot it and then put it in waiting mode, and then the big reveal is I'm gonna continue instead of stepping and just see what the circuit does. All right, so if you can see my circuit, so if I followed the instructions, what happens is they come on in a sequence. You can see it right there on the camera. They come on in a sequence, and then they go off in a sequence. That's the E-OR part, is just toggling them. So toggles them on 1, 2, 3, 4, 5, and then off 1, 2, 3, 4, 5, on 1, 2, 3, 4, 5, off 1, 2, 3, 4, 5. That's what that does. That's completed lab. There is one thing I didn't do, which I'll leave for you if you want to try it, is turn them all off. I should have said just turn them all off here, but turn them all off when you reset the counter and have it start over, as opposed to sort of lighting up and then lighting down. You could light them up, turn them all off, and then light them all up again, and then turn them all off. That's totally up to you, but this is functioning as it's supposed to function. Hopefully you can see that okay. Which is pretty dang satisfying, I gotta tell you. To me, anyway. Okay, so what I'm going to do right now, let's see, I don't know, what do you want me to do? You might ask, I can put the homework answers back up or some portion of them. I can answer your questions on chat. Anyway, so I'm going to sit here for a few minutes and I'll get your feedback on chat. Otherwise, that is what I have for today. Thursday is all Lab 10. It's going to require some changes to this circuit. We're going to add more lights. So I might change colors, but mostly I'm going to leave the circuit alone, and then I'm just going to add more lights. And I might change colors while I'm doing that, but that's, and then I'm probably going to need to wire them to different ports based on the diagram. So anyway, I'll start with that on Thursday, as I'll wire up the new diagram. Building off of what I currently have from Lab 9, and then we'll start coding it, and it will use comparisons and branches and stuff like that. So thanks for being here this morning. I do have sort of an office hour broadcast on Wednesday morning at 10. If anyone wants to drop in on that for any reason, I can answer questions. And then otherwise I will be back here on Thursday at 8:30. Now is my time to sit here quietly and wait for questions. So I'm going to answer it in chat too, but You don't actually need to do a comparison there because you already know R5 is 0 once you get to 9B. You're already in that section where you just did that. So really the whole thing, don't move 0 to R2. Do a bit clear on R2 for the appropriate pins. That's really all you have to do. And you do need that store. I forgot. Yes, you're going to need that store. A BIC and then a store. Should do the job, I believe. So the start delay label doesn't determine the time delay. The start delay label, all it does is give you a location. That just means this is the part of the program where the delay loop is going to happen. It doesn't do anything. Labels don't do anything. It just gives you a location you can branch to because you're ready for the delay part of the program to hit. And if you look at the delay loop itself, it's got a conditional branch in there. So it's actually looping until R4 becomes 0. So as long as R4 is not equal to 0, it will continue this delay loop, which counts down one at a time. But start delay doesn't actually do anything other than give you a spot where you can branch to, which allows you to control this switch statement above, where you're testing R5 to see if it's 1, 2, 3, 4, or 5. You have to have some way of getting out of that switch so that no other parts of the switch execute. So that's really what start delay does, is give you a way to get out of the switch. Oh, and I'll also, what determines, by the way, the value on line 121 is what actually determines how long the delay is. So all that is a value that counts down from there to 0. So the bigger the value, the longer it takes to count down to 0. So you can make this delay be longer by making that value there on line 121 bigger, or you can make the delay smaller or shorter by making that value smaller. It's an interesting thing to sort of fiddle around with and see what it feels like. Small changes, by the way, like just making it 1. So the lab part 1, is it lab 9 part 1 that you're talking about? So it'll come up here in a second. Question 1, hopefully, is what you're referring to. Okay, yeah. All right, so I have the right part on the screen. It's about to come up on the screen.